All right, the next section that we have is 16.4, parametrized surfaces and surface integrals. First thing we want to do is take a look at what a surface parameterization is and how it relates back to the only other parameterization that we've worked with, which are, excuse me, path or curve parameterizations, what I like to call a path. Um, we are at least should be at this point, very well versed in how to construct these, how to think about them. We've had lots and lots and lots of practice with it. The key observation here is that because we only have one parameter, so I'll write this down. This says that, so here there is one parameter. So that means if we only have one parameter, in other words, like one variable, one thing that's changing its value, then this R of t, the only thing it can produce at best or at most is a curve, something one-dimensional. So one parameter, this produces a one-dimensional thing, a one-dimensional object. So a one-dimensional. Technically, we could say the word manifold, but really this is a one-dimensional thing. In other words, a path or a curve. What we're going to do is move up in dimension. Our goal is to not just draw some curve in 3 dimensions, but maybe draw a surface in 3 dimensions, like a cylinder or a sphere or a paraboloid, something like that. So that is the motivation for having a second degree of freedom. Instead of one parameter, moving up here where we actually have 2 parameters now. So let's just notice that here we've got 2 parameters. So 2 independent parameters. So this will produce a 2-dimensional manifold or a thing, i.e. a surface. What we usually think of when we hear the term surface, we automatically think of a 2-dimensional surface. In mathematics, we can think of a curve or a path as a 1-dimensional surface, a point or a dot as a 0-dimensional surface, and so on and so forth. But here, this does produce a traditional, what your everyday person thinks of when you hear the term surface. So just like the case with our usual parameterizations of one variable, one parameter, we have components here. And each of these components tells us what the x's, y's, and z's are on our surface. And these in general are just functions of our 2 variables, u and v. All right. So let's go ahead and get started here and look at example 1, which is to find a parameterization for the cylinder of radius r. So I've went ahead and I've went ahead and created another video that starts this section off. If you haven't seen it yet, I'd suggest you go look at it. And it's a way to build intuition on parametric surfaces and how we might construct them and how we get these equations and how we should think about them. So if you watch that video first, this example should be a breeze after watching that video. So I'm going to go ahead and assume that you have watched it. If not, pause this video, go back and watch it. But I will briefly restate. But if you want more detail, I would look at the video. So essentially, if we want to parameterize this cylinder, let's go ahead and just add something in here that I don't have written down. Let's just go ahead and add because this cylinder, right? This cylinder, it extends forever in the z direction. It goes forever upward and downward. So let's go ahead and just chop that off and say, how about for z between, let's say, 2 and 4. Okay, let's go ahead and say 2 and 4. So in that case, what we want to think about here is If it helps us, we can get a visualization of it. We can sketch it. You can also use a graphing utility such as CalcPlot. So here's a graph. Here's a little graph here. And then we're going to go ahead and say we've got a cylinder right here. And it does something like that. So this is a height of z equals 2, and the top we've got a height of z equals 4. So the way that I would think about this is we can think about this as how would we draw this? We can think of starting at the very bottom of the cylinder. At any point on the bottom circle, if we take the slice of the bottom of the cylinder, our cross section is a circle. So pick a point anywhere on your circle to start. I'll probably start right above the x-axis, so like right here. And then imagine just tracing this circle. Then maybe we would increase our height a little bit. So if we start off at 2, maybe we hop up a little bit and go to like 2.1. So we're a little bit above it, and then we're going to go ahead and draw another circle. And we move up again and we draw another circle. We move up again and we draw another circle. And essentially, we're going to work our way in an orderly fashion from z equals 2 to z equals 4. And at every single step of the way, we're going to draw a full circle. So if we think about that as a continuous process, as this procedure, that will, in fact, draw for us the cylinder. So let's think about it here. So for instance, if we kind of write this out as a process, so the vague idea or the vague process is the following. So let's say start at z equals 2 and do the following. First thing is that, really there's only one step here. We're going to start at z equals 2, and then really our instructions would be to draw a circle of radius, in this case, capital R. So let's think about this now. I'll draw this in red. What does a parameterization look like for a circle of radius R? Well, in this case, let's go ahead and say R is, let's say R of, let's go ahead and say T for now, just because this is a one-dimensional parameterization. Let's just keep it familiar. So if I'm at a z value of 2, I know my z component's just 2. Now if I have a radius r, I know I'm going to have r in front of my sine and cosine terms. So I should have something like r cosine t, r sine t, and that will draw a circle of radius r at a z value of 2. And then the next thing we'll do is I'll just say increment z. So maybe we basically take our old z value and move it up a little bit. Maybe we increase by some small amount, like 0.001. Something like that. So we move up. And this is basically going to be a loop. This process just repeats itself. This tells us some initial value to start at, and then we are going to simply loop like this. Take our new z value, draw a circle of radius r at that new height. Then we're going to bump z up, lift it up a little bit, and then return back here to this draw step. And we do this until, so maybe I'll just say here, I'll add down here, stop at z equals 4. All right. So with that being said, that's sort of the outline or the process that I have in my head. I kind of think of it as this like program. Like if I were going to program this or script this in like some sort of language, I'd use a loop or something. I also think about it as maybe a 3D printer. If you think of a 3D printer, The printing head would start at the location, the lowest location, and then it would print in a circle. And then once it returns back to the starting point of that first circle it drew, and then the printer head would lift up a small amount. And then it would draw another circle. Lift up, draw another circle, lift up, so on and so forth until it reached the final height. All right, so essentially what we can see here is if I were to draw a few of these, let's say our increment for z, let's say our change in z were, I don't know, something like 0.2, whatever. So then the first couple parameterizations, the next few parameterizations would look like the following. We would still have our, maybe I won't draw the r of t, I'll just go ahead and say this would still be r cosine of t, r sine of t, but now this would be 2.2. And then the next one would be r cosine t, r sine t, and then 2.4, and yada, 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 so on and so forth. You get the idea. Eventually, what's really happening here is this z component needs to be a variable because it's changing. And that's exactly, if we look up above here, we now, for a parameterization of two variables, have access to two independent variables, two independent parameters. So really, what we were calling t down here, our one variable, we can just say u if we want to. And then this z value, we'll just put v. So this should give us the following. R of u comma v equals r cosine u, r sine u, and v. Okay. Now, we'd have to say a domain. So for u comma v in the domain, well, u is between 0 and 2 pi, since we have to trace a full circle, and v is between 2 and 4, because that's the range of z. And there we go. That's our parameterization.